Before we move on to semiconductor devices, we will just have a look at like wires and switches. Like often we disregard them, we take it for granted, but like we'll have to take those into consideration as well. So probably let's get started again. Like when I say we have to talk about wires, like I'm talking about the resistance in those wires. So you would have recognized this formula from module 1. So resistance equals rho times length of the resistor by the area. So this is the formula from the previous module. So there, like we also had a table which displayed different materials, like along with the conductors. We also had semiconductors and insulators and all their resistivities in ohm meter. Often, again, here in North America at least, like we don't use ohm meters, like we use Siemel ohms per feet. So CMO is a circular mill, which is the area of a circle, because again in wires, like mostly everything is circular, like it's a cylinder. So we take the area and of a circle, and we call C mills. A mill is 1/1000th of an inch. So circular mill is a area of a circle with a diameter of 1 mil. So that is a circular mill. So here are the resistivity of conductors, or like the wires, in Siemel ohms per feet. So again, feet is another unit like that we use often. So this is the rho values for those. Okay, and let's do another math here. Again, like we use, although we say CMOL, we don't use CMOL directly. We use something called the gauge, or like the American wire gauge, or gauge, however you want it to pronounce. So the wire gauge is what we use here. So if you wanted to buy a extension cord, or like a power bar or something like that, like usually like they are I hope you're not buying any other say wires like that are big enough to, like, say wire circuit. Like I better like you leave those to the professionals. But again, like if you when you purchase all these, you will have to make sure that the voltage doesn't drop too much. So if the you would generally observe that if a power bar has a longer cord, say a 30 meters power bar, or like say 30 meters extension cord. So usually like the wires are going to have like the wires are going to be like bigger, like means like I say in terms of diameter. So it's because like the bigger wires like has lower resistance, right? Like say if you have more resistance, it's going to drop the voltage. Let's say 120. What we expect is, like say if you have a socket which provides 120 volts, and if you use a extension cord to power a power device, and at the end of the circuit, or end of the extension cord, you should still be able to get like a reasonable voltage. So a reasonable voltage in general is, it should be at least like say 3%. The voltage drop should not be more than 3%. That's what we expect. So the resistance of the wire is like becomes like very important here. So that's when we use this. So here you can use we know CMOL. So from the previous table, we know the formula of or like the constant rho, the values of for those for different material like copper or silver or gold or something like that, and that in Siemel ohms per foot. So and we need to know the area and CMIL. So how do we get the area and CMIL? So there is a DigiKey conversion app, so which you could use, or there's another formula you can use as well. If you have in wires, like it is like a linear formula, you just have to plug in those numbers and get it. So but like this is much easier, so you can go there, plug in like how much what is the wire gauge, and then like you just plug those numbers, and then like you get the CMIL. And once you get the CMIL, you can calculate the resistance of that particular conductor. So here again, an example. Calculate the resistance of a 1,000 feet 12 wire gauge copper wire. So the copper wire has a resistivity of 10.37 CMIL ohm per feet, and using DigiKey converter, like for 12, my bad, just give me a second. So using the DigiKey converter, I got the area that is 6530 CMILs. So now I just have to plug in those numbers. So the resistivity of a copper conductor is like 10.37 times 1,000 feet, that's the length, and then it is going to be divided by the CMILs. So this is the resistance, and let's say if you know the current like that is flowing through this circuit, then you can also calculate the voltage drop. Okay, so that is what we will be doing in the assignment problem. So let's move to the assignment problem 2.4. Calculate the voltage V2 in the circuit below if the load was connected to a main, connected to the mains with 14 wire gauge wire, and wire, and it draws a current of 10 amperes. So what is the voltage V2? The load is located 100 feet away from the mains. So the way you will have to calculate the voltage drop here. So let's say here is the mains, and then you run a wire to a load, like this might be a socket, and then you have a load, a resistive load here, and this one draws a 10 amps current. Okay, so what is the voltage drop here? So this is a simple circuit I've given you to calculate the voltage drop here. So this is the load. We are not really worried about like what this load is, because I just wanted to know the voltage drop across these. Okay, but what I need is like 10 amps of current is flowing through this. So what I would do is calculate, okay, for 14 wire gauge, what is the CMIL? And then we know for a copper wire, like I hope this is a copper wire, right? A load. Okay, the load was connected to a mains with, okay, what wire? Like I didn't mention like what wire it is, but like say we will assume it is a copper wire. Okay, so for copper wire you can use the same resistivity here, like 10.37 CMIL ohms per feet. So once you have that, and once you have the CMIL of a 14 American wire gauge wire, then what you do is you calculate the resistance, and 10 amperes of current is going to flow through that. So you will multiply, you will find out the voltage drop here. So voltage drop is going to be V is equal to IR, right? And I, 10 amperes, and R, the resistance, and that is going to be the voltage drop across this wire, and you will also have a voltage drop across these, right? So you just have to subtract these two voltage drops from 120, and then you will get the voltage that will appear across the load here. So that is how you solve 2.4. So that should wind up the wire. So this is an important calculation again. So when you're buying a extension cable, and if you know how much power current you will be drawing, make sure you just take this into consideration. Usually these things will be mentioned on the extension cable. So what is the maximum current you can draw from the circuit? So based on that, like say if you see if you wanted to connect a very high current load, then the wire will be automatically like thinner as long as you go longer and longer. So let's say a 10 amp wire, which is just like say maybe 5 feet, would be like say a little smaller, like it will not be a bigger wire. As the distance goes up and up, so from 5 feet, if you move to 10 feet and 15 feet, 20, 30, and if you go like that, then like you will see the conductor's diameter like increasing. You will have like bigger wires actually. So that is because they had to take into consideration like how much voltage will drop in the wire. So that is that is like very important like when you buy an extension cable. Okay, and let's move to the next section, that is switches. And we will in this course, like you will have to know about switches, but again often we'll be using a push button or like or probably like sometimes we just like connect the wire and like remove the wire, so that sometimes we do that as well. But like we might be often using push buttons, but like there are other switches. There are also rotary switches. So the switches, push button contains at least like 2 contacts, and which is like either closed or like say open. So that is the most important thing you will have to understand. So sometimes like say normally we call it like normally closed or normally open switches. So which means the contact, the push button has like a spring like that is like kind of pressurizing actually. So it is going to be either in contact. So when you press it, like you will turn it off, and then like when you let it go again, like it kind of like turns on again, and you need this external pressure to turn on and turn off. Okay, but like it can either be turned on without any external pressure or turned off without any external pressure. So you will have to check those before you buy a push button. The ones which we have in our kits are usually like it's turned off when you don't apply any external pressure. So that's the most common ones like which we have. But again, there are options that is available the other way around as well. A switch contains at least 2 contacts, which is open or closed when the external lever or knob is flipped or moved. So that is a switch. So you will either have a lever or like a knob for these. So that is a switch. A rotary switch, again, like we talked about a potentiometer, like very similar to that, but like again, in a rotary switch, what happens is you are just like making an electrical contact actually, like say in a rotary fashion. So some cars, they have, say for example, the volume button is actually a potentiometer, like so you can smoothly, it varies continuously, but if it moves in discrete steps, most probably those ones are like rotary switches. So it kind of like moves in a discrete way. So those are all like rotary switches and not a potentiometer. So it is important to understand the difference between a potentiometer and a rotary switch. And poles and throws. So when you get a switch, you have to understand these. So they used to say SPST switch, SPDT switch, or DPDT switch. So what does all these mean? So poles means the movable contact in a switch. So how many movable contacts you have determines the pole. So for example here, each pole is required for like say can I say a circuit? Because a circuit is like say only when it is closed. So when it moves, it becomes it is not a closed. So yeah, we can say a circuit. So this is one circuit, like one pole, one circuit. So it makes one contact. Like so, if you have just one movable contact, we call it single pole. So here you have 2 movable contacts, so we call it 2 poles. But again, the thing is, like both of these are attached together. So when you turn on and turn off, like both of them are going to move and make contact. They are not independent, they are attached. So that's why we have the dotted line here. Likewise, you also have single pole double throw switch. So double throw switch is the number of contact that a switch makes actually. So sometimes you will have 2 circuits. So let's say I have, this is sometimes called a three-way switch as well because it has three contacts. So let's say I have power running through this. So I have one light bulb connected to one T and another light bulb connected to the T. So when I put it in one position, one bulb will be turned on, but when I turn off, or like when I move it to the other position, another light bulb turns on. So there are like things like that. And sometimes positions are also important. So sometimes this could have three positions. So this is position 1, this is position 2, but like you might have a position where it just stays in the center and like it turns off. So turn on a light bulb here, like let's say light bulb 2, light bulb 1. So in this position, light bulb 2 is turned on, and as soon as you move, light bulb 1 is turned on. But like some switches will also have a middle position where both the light bulbs are turned off. So that is possible. So exactly the same thing, double throw switch. You can also have two poles. So double pole, double throw switch. So that is poles and throws. Again, this can be like even if you buy switches for your home, for household applications, these are like very important to know. So here is a three-way circuit. So I hope at least like say your homes should at least have like one of these circuits actually. So in the end of the hallways, or like say a staircase, you have say a switch in the bottom and a switch at the top of your staircase actually. So you can turn on when you're downstairs, and then like you come up and then turn it off. So you might have at least like one circuit in your home actually. So that works because of this three-way, or like say three-way switch. So what happens, or like how it is wired, is this is the circuit. So you have the line, which is the power, like the phase coming in, and the neutral is connected to the bulb. So what happens to this line? So it comes to the contact, and then like say it comes to the main contact, and then you have two other contacts which are connected together. So one of these switch is downstairs and the other switch is upstairs actually. So what happens is like you flip the switch in the bottom, so at that point of time it turns on, and then as soon as you go up, you just turn it off, and then like say you can go. So that is a simple three-way wiring with a single pole double throw switch. That is one of the applications. And we have the semiconductor devices now. So we will talk about semiconductor devices in the next subsection.